Hello. Today we're going to talk about chapter 26, Inferences for Regression. So this chapter is going to be revolved around percentage of body fat and waist size. So here you've got a scatter plot, and we want to model that relationship, and we can see that it's a linear relationship. And we've done that before, but here we're going to take it a little bit further. Okay, we're going to do what can the model tell us beyond that? Okay, so we're going to make confidence intervals and we're going to test hypothesis about the slope and intercept. So before, we found a confidence interval for a mean, and we can imagine a single true underlying value for that mean. Okay, then we tested whether two means or two proportions were equal, so we imagined a true underlying difference. So what does the inference for regression mean? This is when we break it down into kind of like smaller pieces. We know better than to think that even if we knew every population value, the data would line up perfectly on a straight line, right? So in our sample for just the 38-inch waist, here's our distribution of percentage of body fat. Okay, so now we're going to do that at each waist size. When we do that, we can get a distribution like this. So you have, individual distributions at different waist sizes, and then you kind of draw a line through that mean. Okay? So it assumes the means of the distribution of body fat for each waist size. Okay? The model isn't perfect, just like everything, right? It's never perfect, but it might be useful. If we had all the values in the population, we could find the slope and intercept of the idealized regression line explicitly by just using that least squares regression, what we've done before. Okay, but we don't usually get the entire population. So we're going to chunk it. Now, of course, to write your linear regression line, we're going to have our parameters with beta and typical line. Just notice the variables. Now, not all the individual y's are the means, okay? Just like before, our x's are going to have those averages. When we plug them in, our data might fall above or below that line, okay? So here, we have to talk about the individual y's instead of the means, so we have to add a error, okay? This equation is now true for each data point, so that error is just kind of making for that adjustment. As always, there's assumptions and conditions. So in chapter 8, we checked the straight enough condition. Here, we're going to make more assumptions because we want to make inferences about the coefficients. So we've got more things going on. Now, be careful, go in order, because if the first thing in the list isn't true, then it doesn't make sense to keep on going. Okay, so try to go in order when you do your assumptions and conditions. The first one is, of course, the straight enough condition. We use that by checking the scatter plot. Okay, if it's not straight enough, then you consider re-expressing the data. Okay, a couple ways to do that. We've done that before. Now, make sure it's quantitative data condition, all right, because we're doing linear, so make sure both are quantitative data. The independence assumption, the individuals are representative sample of the population, okay, so the randomization. You can check the residual plot to make sure that things are scattered, okay. Number 3, does the plot thicken condition? You check the residual plot, make sure it's uniform, right? You don't want a whole, like a bigger cluster here than over here, okay? And want to be fairly even like this. Then you have the normal population assumption, so your nearly normal condition. So you can check the histogram of your residuals. Now, remember, you're doing this for each one, right? Each one of those waist sizes, okay? And always, I don't know why people forget to do this, check for outliers, okay? It's important. If all 4 assumptions are true, this is what it should look like, right? Perfect normal distributions, the line going through the means, it'd be perfect, okay? Okay, Here's the catch. The best way to check many of the conditions is with the residuals, but we get the residuals after we make the model. Okay? I know, it seems weird and seems counterintuitive to not do the conditions first, right? So think about it. Work in this order. Make a scatter plot, check the straight enough condition. If the data is straight enough, fit a regression model and find the residuals and the predicted values, so your y-hats. Make a scatter plot of the residuals against x, or the predicted values. Should have no pattern. Okay. If the data are measured over time, plot the residuals against time to check for evidence of patterns. If the scatter plots look okay, then make a histogram and normal probability plot of the residuals to check the nearly normal condition. There. If everything's satisfied, then you can go ahead with inference. So let's do an example. So here, take a minute, read this example about craters. This was in the book. And we're going to check the assumptions and conditions. So here are the answers. You have your linearity assumption, so the straight enough condition, which looks good. The independence assumption, the sizes of impact craters are likely to be generally independent, right? Different meteors. The randomization condition, well, these are the only known craters. So there's ones we don't know, like ones that have hit the ocean, okay? So, which, you know, the ocean takes up majority of Earth, so there's a lot we're missing. So don't be too general, or too specific with your conclusions, okay? But we work with what we have. Random residuals condition, the residuals appear to be randomly scattered, okay? 2 points seem a little off, but doesn't seem like a serious violation. So we're just going to let that one kind of go. And then the nearly normal condition, it suggests a bit of skewness in the distribution of the residuals, okay? But it's not serious enough. Like, it's not a major skew. So we're just going to keep going, okay? Nearly normal is exactly what it sounds like. Now, we expect any sample to produce a slope whose expected value is the true slope, okay, capital beta. But what about that standard deviation? And what aspects of the data affect how much the slope and intercept vary from sample to sample? So now we're going to talk about how the slope and the y-intercept can vary. All right, so let's talk about the spread around the line. So basically the scatter. All right, less scatter, okay, so means the slope will be more consistent. So see how this one has less movement around the line? That slope will be more consistent. Doesn't matter which points I take, I'll roughly get the same slope. Over here, depending on my samples, which ones I choose, my slope can vary because there's more wiggle room, right? Think of it like that. Now, the spread of the x's, okay? So a large standard deviation produces a more stable regression. Well, that's exactly what's happening. The spread of this x is only from here to here, but this x is from here to here. It has a much larger spread, so a larger standard deviation, so this is going to have the better line. Okay, now, let's see, having a larger sample size gives more consistent estimates as well. So the more data, the better, right? That's usually how it always is. So there are 3 things that affect the slope. So the standard error for the slope, you have the spread around the line, the spread of the x values, and the sample size. All right, so the formula is this, but you should never have to calculate that by hand. Okay, I'm certainly not going to make you. And when the conditions are met, the standardized estimated regression slope would be this formula, you know, following the t-model with n minus 2 degrees of freedom. Right, we're subtracting 2 here. We estimate the standard error with this formula, okay? And then n is the number of data values, Sx is the ordinary standard deviation of those x values. Of course, the same reasoning applies for the intercept, so we can write it as this, but we rarely use this fact for anything, okay? The intercept usually isn't interesting at all, okay? As you've seen when we've talked about some data, most of the time the intercept is useless. You know, you don't want to calculate zero height, okay? Most hypothesis tests and confidence intervals are about the slope. All right, so let's do an example based on researchers in the food science. So read this, and here we have our output, a statistical output. So number one, what does the t-ratio of 3.27? Well, that's right here. For the slope, tell us about the relationship. How does the p-value help your understanding? Well, a high t-ratio indicates the slope is different from zero. Okay, it's not zero. Okay, that is that there's a linear relationship. Okay, the small p-value, right, 0.0018, means that it will be very unlikely to occur based on chance. So, yeah. So number two, would you say that measuring a person's height could reliably be used as a substitute for the Wetter method of determining how big a person's mouth is? Well, hopefully you said not really, because of the r squared, right? We know what r squared is. So 15.3% of the height, our height doesn't account for very much of the variability. Okay. What does SE? Okay. That value of S tells the standard deviation of the residuals. So mouth sizes have a mean of 60 and a standard deviation of 15.66. All right, so if that's the standard deviation, then having errors 15 to 30 cubic centimeters off would be very common. All right, now the standard error. So in context and repeated sampling, we estimate the slopes of the lines predicting mouth volume would vary with a standard deviation of 18.77. That's right here. So the standard error of your slope, okay, would be 18.77. So that's how much my slope's going to vary off from. All right, so here we have a null hypothesis of zero. Slope questions the entire claim of a linear relationship between the two variables, often just what we want to know. So we test whether the slope is zero, and we continue as we would with any other test. And the formula for the confidence interval is this, which looks awfully familiar. Okay, so we have a useful regression. Now we have to predict, okay, without being irresponsible, right? So now we have standard errors, so those are important to help us construct a confidence interval, which allows us to report uncertainty honestly, okay? Instead of just saying, hey, it should be this, we're going to give you an interval because that's better, right? Statisticians never want to say exactly because we don't want to be proved wrong, right? Because I always want to be right. It's fair. I do. All right, so not always, but I try. So for our percentage body fat and waist size example, we have two questions. Do we want to know the mean body fat for all men with a waist size of 38 inches? Or do we want to estimate the percentage body fat for a particular man with a 38-inch waist? Okay, it's the same. The predicted body fat is the same in both questions. Okay, so they're similar questions, but we can predict the mean percentage body fat for all men whose waist size is 38 inches with a lot more precision. Okay, so that's why we like that question more. Well, we start with the same prediction in both cases. So we're predicting for a new individual, all right, going back to those same two questions, one that was not in the original data set. We'll call his value this. The regression predicts his body fat as this, right? You have your intervals take this form, but the standard errors will be different for the two questions we posed. Okay, so while it starts off the same with both of those questions, the standard error is going to be different. So the standard error of the mean predicted value, so the average predicted value is this. Well, individuals vary way more than means. So the standard error for a single predicted value is larger than the standard error for the mean. Okay, so what I predict for a person is going to vary a lot more than what I predict for the population. Think of it like that, okay? So you have two kinds of confidence intervals. The narrower interval, the smaller one, is for the predicted mean value. The wider one is for an individual. Okay, understand the wording. This is what I mean by statistics. It all sounds the same, but it's not. Okay, it's the same but different. I know, it's confusing, but just keep practicing. I promise. You'll get better. I'll get better. So here are our confidence intervals. So look at the difference between predicting a mean and an individual. The green lines show the 95% confidence interval for the mean predicted value, and the red lines were predictions based on individuals. Okay, so it's very different. So what can go wrong? Okay, don't fit a linear regression when it's not straight, right? Linear, the root word there is line. No joke, have had people not realize linear meant a line. Okay, I want you to notice that. Okay, watch out for the plot thickening. If the spread in y changes with x, our predictions will be very good for some x values and very bad for others. Okay, make sure the errors are normal. Check the histogram and normal probability plot of the residuals. Always check these things. A lot of people don't like checking them, but they're quick fixes or quick checks. Okay, you got to make sure things are good before you start doing all the math. Watch out for extrapolation. It's always dangerous to predict outside your range. Okay, watch out for high influence points. Oh yeah, those outliers. Okay, everybody forgets to check the outliers. Okay, and no, they're not just based on what it looks like. Okay, watch out for one-tailed tests. Okay, tests of hypothesis about regression are usually two-tailed. So software packages report two-tailed p-values. So be careful. If you're using software to conduct a one-tailed test about slope, you'll need to divide the reported p-value in half. All right, I know we're not going to be using statistical software, but you should check that for your graphing calculator. Oh yeah, that's why it's useful. Good to know. All right, so what have we learned? All of this good stuff. Okay, so recap. Hopefully this makes sense. If it doesn't, I'm in class. I'd be happy to go over it again.